So now that we've given an overview of the structure and functionality of the server components, let's dive into how they're implemented. And we'll take a look at the LockManagerController and the LockManagerService. As you would expect, the LockManagerController isn't the interesting part. It's the service that's the interesting part. And you can get that here at this link in my GitHub repository, which is part of the EX1 project in the WebFlux folder in my Live Lessons GitHub repository. So here we are on the server side of all this stuff. Let's just take a quick peek at the LockManagerApplication. This is actually somewhat interesting. So it's got the main entry point that we always see here, where we just take the main method and run the Spring application, passing in the LockManagerApplication class and some arguments, if any. But this is where it gets more fun. So what we've done here is we've added a couple of beans to this implementation, which tell Spring to use Java virtual threads to handle all the incoming HTTP requests. If we don't do something like this, it'll continue to use the servlet thread pool, which is what we had done in the previous example using Spring Web MVC. But now we want to be able to do this using the virtual thread. So we make this async task executor that makes a new virtual thread per task executor. And then we go ahead and we have this protocol handler set up to use new virtual threads per task executor as well. So that means that the threads that are running inside the pool of the threads that are running when a request comes in to service the request come from the virtual thread executor that makes a new virtual thread. And when we look at the output from running the test, you'll see that the whole thing is now running in virtual threads. Let's take a quick look at the controller. As I said before, there's not a lot of interesting stuff here. It's what you'd expect. It's got an auto-wired service, and it's got the various methods that create the semaphore with an initial count and then have acquire and lock methods, and they just return the appropriate types that are reactive types like mono for create, mono for acquire, flux for the acquire that takes a permit count, and so on. So all those things are very straightforward. This is where it gets fun. So let's go ahead and take a look at the LockManagerService. So as with the LockManagerService from the previous example using Spring Web MVC, the WebFlux version also uses an array blocking queue, so we can be very clever about implementing this distributed semaphore semantic without having to think about synchronizers per se. Here is the create method. This is actually identical to what we had done before in the previous example. It takes permit count as the parameter, checks to see if we've been initialized before or if the permit count that's being requested is not the same as our previous initialized array blocking queue. Depending on what we get back from that, we're either going to clear things out and or restart with a new array blocking queue with the appropriate permit count and its flag set to true, meaning that we'll have FIFO queuing semantics for threads that are waiting to acquire this. And then we go ahead and call the makeLocks method, which is a factory method that makes us a bunch of lock objects. This is exactly what we did before. And then those lock objects are placed into the array blocking queue. And then we say, hey, something changed if we took this path. Otherwise, we just return false. Notice that we're returning monos. So we either return a mono that emits true if something changed, or we return a mono that emits false if nothing changed. So that means the client can wait, or doesn't have to wait. It can be reactive, and it can get a result back. And then when that result is ready, then it'll go ahead and go on to the next step in the asynchronous chain of processing. Now let's go take a look at acquire. So acquire actually is pretty straightforward. It's more or less the same logic we did before, in that it goes ahead and it basically tries to get a lock. We actually could have done the same little optimization we did before about trying to do a poll first. I probably should make that enhancement. But in any case, we go ahead and try to get a lock. We block here. And we can block, even though this is actually a reactive call, which doesn't like to block. It's perfectly fine to block because we have our own virtual thread. So we have our own dedicated virtual thread to run this. So that if this blocks, nobody cares. It's OK. So notice that we wrap this particular call to take inside of a mono factory method that will return a mono to a lock that will emit the lock when it's available. And we use from callable here because take could throw an exception. And just remember that. It's very unlikely for it to throw an exception, but it could throw an exception. If we get an exception, we're going to log it. And in any case, what happens here is this result is actually returned before this computation runs, which is kind of interesting too. That's pretty straightforward. However, it looked almost identical to what we did earlier. We just wrapped the call inside of a mono. Now let's take a look at acquire that takes a permits count. And this is much, much more interesting. Now, if you recall what we had done before, what we do is we take that count of the number of permits we want, and we're going to make ourselves an array list of that capacity that's going to accumulate the locks as we can get them in a non-blocking way. So the overall idea is very much the same, but the implementation is different. And I had a lot of fun coming up with this solution, and it required multiple iterations between me and ChatGPT, which kept hallucinating crazily and giving me wrong solutions until I finally was able to phrase the question to it in just the right way, and then it gave me a variant of this solution, which I then refined. So here's what we do. We use the from supplier factory method on mono. From supplier is very similar to from callable, which is what we used above, except from supplier doesn't expect an exception to be thrown. So if you throw an exception in here, which we don't, then we couldn't use from supplier. If an exception is thrown, we need from callable. But from supplier is fine if we're not going to be dealing with exceptions. So what we do is we go ahead and we say from supplier, and we call this try acquire lock method, passing in the list that will keep track of the number of locks. So if you recall the try acquire lock method, this is the same implementation we had in the previous solution. What it does is it goes ahead and does a poll to see if we got the lock, and if we did not get the lock, if the lock was null, then we're going to go ahead and give back all of the locks that we've acquired to this point, which could be none, but we're going to give them back because this is how we're going to avoid deadlocking. And then we clear out the acquired locks array list and return 0, which indicates to the caller we didn't make any progress at all. In fact, we went backwards. Otherwise, if we did get the lock, we add that to the list, and then we return the number of acquired locks that we've got so far. And this process of calling the try acquire lock, we want this to keep going until we get a result from acquire lock that equals the number of permits. Here's where things get really fun. So if you recall what we'd done in the previous solution, we had a while loop there. We basically said while try acquire lock, acquired locks, not equal to permits, continue, right? We're just going to keep looping. But that's not the function, that's not the reactive way to do code. Reactive code doesn't like loops. Reactive code likes something else. So here's the reactive solution. This is super duper cool. So what we do is we call this from supplier, which is going to give us a single call to try to acquire the lock. And then we use the repeat operator, which we've talked about before, to repeat this over and over and over again until the result we get back equals the number of permits. So this is basically the way to do a reactive, it's really a reactive do-while loop, if you will, because it calls this thing exactly once initially. So what we're saying is here is call try acquire lock, because we get back this supplier that will do that. Call this repeatedly and keep going until the result we get back equals the number of permits. So that's the super clever way you can do a do-while loop with reactive programming. And took ChatGPT a while to realize that, and I had to frame the question in just the right way to get that. But the thing that made it difficult for me was I didn't really understand how take until worked when I started doing this design. So because I was learning that part as well. Now here's where it gets even more interesting. So what we're doing is we want this thing to repeat until that condition succeeds. When this condition succeeds, in other words, when we have a result that equals the number of permits, at that point, we want to bail out of this repeat loop, using the word very loosely because it's not really a loop, it's the effectiveness of a loop. And what we want to do at that point is we then want to return the acquired locks list, which at that point will contain all the elements that we have acquired. So how do we do that? Well, we use this suppressing operator variant called then many, which I didn't really even know existed till I was playing around with this. And what then many does is it says, wait until we get a result here that succeeds. Then ignore that result and do this operation and return it as a flux. Whenever you see many, it typically means return it as a flux. So what we're doing is we're taking the acquired locks, which have been now set to the right value by this little repeat take until loop, and we then say convert that acquired locks list into a flux using the from iterable factor method, and then return that as the return value from then many, and that is then the return value from the overall method, which returns a flux of locks. So just about the coolest thing ever. I was very pleased because I didn't want to have to write non-reactive code here, but it took me a while to figure out how to do this, but it was worth it, and I think it looks really good and works well. The last piece of the puzzle here is the pair of release methods, release lock, and you can see that what that does is it just returns the lock in a non-blocking way to the array blocking queue and just wraps that in a just call, so it'll return a mono that emits whether we succeeded or failed. And then down here, this is actually another fun little solution. What we do is we take the list of locks, turn them into a stream of locks, and then we go ahead and use the all match method on the stream, which returns true if offer returns true for every lock we're releasing. Otherwise returns false. So we get the result back here, and then we return that and wrap it up in a mono, because that's what we expect to get back. OK, so that is the server implementation. Very fun, very cool, uses a bunch of interesting features, including virtual threads, including these rather somewhat esoteric, but it turns out very powerful features that we saw here. So I had a great time implementing all this stuff.